star delta connection, and here the assumption is primary side is HV and secondary side is LV, which means that on primary side the connection is star connection and which is having high voltage winding, and delta is the secondary side winding connection and which is having LV winding. First let's consider the bank of 3 single phase transformers, and now let's give the notations, as this is the HV side. So HV side notations are in capital letters, and let's consider these as dotted end terminals on both primary sides and secondary side. So on primary side the terminals are capital A2, capital A1, capital B2, capital B1, capital C2 and capital C1. Here A2, B2, C2 are considered as dotted terminals. So coming to secondary side, dotted end terminals are small a2, small b2, small c2, and non-dotted terminals on secondary side are small a1, small b1 and small c1. As now we are considering the star delta connection, means on primary side the windings are connected in star and on secondary side windings are connected in delta. So first let's obtain the star connection on primary side. So to obtain the star connection on primary side, we must join the common end terminals and take the connections on other ends. Here the common ends could be dot ends or could be non-dot ends. So here let's consider the non-dot ends as the common end terminals. So here the non-dot terminals are A1, B1 and C1. So join A1 to B1 and then to C1 and take the connections from dot ends. So this is A2, this is B2 and this is C2. So we obtained the star connection on primary side. Now let's obtain the delta connection on secondary side. So delta connection is obtained by joining the non-dot end terminal of one coil with the dot end terminal of other coil, or by connecting the dot end terminal of one coil with non-dot end of other coil. That is, we can obtain the delta connection by joining the finishing end of one coil with starting end of other coil, or by joining the starting end of one coil with finishing end of other coil. So here let's join the finishing end of one coil with starting end of other coil, that is the non-dot end of one coil with dot end of other coil. So here we are joining the non-dot end of one coil with dot end of other coil, non-dot end of this coil with dot end of this coil. So here non-dot end of C coil with dot end of other coil, and let's take the connections from dot ends. So this is B2 and this is C2 on secondary side. Now let's arrange these windings in horizontal fashion. So let this be the HV winding and these be the dot ends. So here A2, B2 and C2, this is A1, B1 and C1. And now consider the LV winding, and the terminals are, and let these be the dot end terminals. So dot end terminals will be small a2, small b2 and small c2, because this is LV winding. So this end will be a1, small b1, small c1. Now make a note that on primary side we are having star connection, means we need to obtain star connection, and here star connection is obtained by joining the non-dot end terminals, and we took the connection from dot end terminals, means join the non-dot end terminals like this. So we obtain the star connection on primary side. Now let's obtain the delta connection on secondary side. So observe that here we got the delta connection by joining the non-dot end terminal with dot end. So non-dot end terminal with dot end, so non-dot end terminal with dot end and non-dot end terminal with dot end, and we are taking the connections from dot ends. So this is how the delta connection is obtained on secondary side. Now let's draw the phasor diagram for primary side winding. So let's consider the primary side star connected VA phasor like this. Now we need to decide the terminals of VA phasor. So terminals of VA phasor are A1 and A2, and connection is took from dot end, that is A2. So arrow will point towards A2, so the other end will be A1. Now we need to draw the VB phasor, and we know that in three-phase balanced ABC system, if VA is at an angle 0 degrees, then VB will be at an angle minus 120 degrees and VC will be at an angle 240 degrees from VA. So VB will be at an angle minus 120 degrees from VA. So as this is negative angle, means in clockwise direction at an angle minus 120, we will have VB, and the terminals of VB phasor will be B1 and B2, and the B2 is the connection we took from, so the arrow will point towards B2. So here this will be B1, and now at an angle minus 240 degrees there will be VC phasor. So in clockwise direction from VA at an angle minus 240 degrees, draw VC phasor, and the terminals of VC phasor will be C1 and C2, as C2 is the connection we took from, so arrow will point towards C2, so this end will be the C1. So here capital A1, capital B1 and C1 forms the common end terminal, and let's represent that with capital N. So we obtain the phasor diagram for primary winding connections. Now let's obtain the phasor diagram for secondary winding connections. So secondary side phasors are drawn parallel to primary side phasor. So let's draw the secondary side VA phasor parallel to primary side VA phasor, and now we need to decide the direction of secondary side VA phasor. And observe that here on primary side the connection is took from dot end, and now observe the secondary side winding connection. Here also connection is took from dot end, means the direction of secondary side phasor will be same to that of primary side phasor. So we are taking the same direction, and now we need to decide the terminals of secondary side VA phasor. So terminals of VA phasor are A1 and A2, and output is taken from dot end, that is A2. So arrow will point towards A2. So this will be the A1. Now observe in winding connection that small a1 is connected to B2. So here to A1 there will be B2, and small a2 is connected to C1. So to A2 there will be C1. Now let's draw the secondary side VB phasor. First let's draw the VB phasor somewhere parallel to the primary side VB phasor, and now we need to decide the direction. So as here the connections are took on dot ends on both primary side and secondary side, means the direction of secondary side phasor will be same to that of primary side VB phasor. So we took the direction like this, and now we need to decide the terminals. So as B2 is the connection we took from, so arrow will point towards B2, so other end will be B1. So now coming to this phasor diagram, observe that A1 is having B2 end, so this phasor must be drawn like this. So this end will be B1, and now let's draw the secondary side VC phasor, so which will be parallel to primary side VC phasor. So primary side VC phasor is like this, so let's take the secondary side VC phasor like this. Now we need to decide the direction. So observe that on primary side and secondary side the connections are took from dot ends, so the secondary side VC phasor direction will be same to that of primary side VC phasor. So this is the direction. Now we need to decide the terminals, as here on secondary side the connection is took from dot end terminal, that is C2, means arrow will point towards C2, so the other end will be C1. Observe in secondary side phasor that A2 is having C1 and B1 must have C2. So this VC phasor is drawn like this. And now we need to decide the phase 2 neutral voltage in delta connection for comparison purpose. So here in secondary connection the connection is took from A2 terminal. So A2N is the phase 2 neutral voltage in secondary side delta connection for comparison purpose. So these are the phasor diagrams for this star and delta connection. Now let's identify the vector group symbol. In vector group symbol, first character is capital letter and it will indicate the HE winding connection, and here we took the primary side winding as HV winding and this is star connected. So in vector group symbol, first character is taken as capital Y. And now the second character in vector group symbol is in smaller case and that will indicate the LV winding connection. And here we took the LV winding connection as delta connection. And so the second character in vector group is represented with small d. And the third position in vector group symbol is a numerical and that will indicate the LV side phase to neutral voltage displacement with HV side phase to neutral voltage. And now observe the primary side Phasor diagram that here the phase to neutral voltage is A2 capital N, which is taken as reference and which is represented with minutes needle in clock. So represent this A2N phasor in clock with minutes needle, and as this is taken as reference, this minute needle will always be at the position of 12 in clock. And now come to the secondary side Phasor diagram in delta connection. We know that in delta connection there will be no neutral connection, but for comparison purpose we need to consider the imaginary neutral. So here we are taking the imaginary neutral and now the phase to neutral voltage is small a to n and that is represented with hours needle in clock. So if you superimpose this on this, the minutes needle will look like this and hours needle will look like this. So if you place 12 here, then this position will be 1. So minutes needle is shown pointing towards 1. Means here the numerical in vector group symbol will be 1 and that will indicate the phase displacement angle between LV voltage and HV voltage, which is the angle between minutes needle and hours needle. So here the angle between minutes needle and hours needle is 30 degrees and as this hours needle is right side to 12, it is considered as minus 30 degrees. So 1 here from clock notation will indicate that LV side phase to neutral voltage lags behind the primary side phase to neutral voltage by an angle of 30 degrees. There are 4 possible connections of star delta connection, that is we can obtain star delta connection in 4 ways. One of the ways is this connection. Now let's see the other possible connection of star delta, and in that let's leave the primary side connection as it is and the change you will observe in secondary side connection. So here in delta connection, instead of joining the non-dot end with dot end, let's join the dot end with non-dot end and take the connections from A2, B2, C2 as usual. So let's join the dot end with non-dot end and dot end with non-dot end and dot end with non-dot end like this and take the connections same as that of the previous case, that is from dot ends A2, B2 and C2. Now let's draw the phasor diagram for these connections. So as the primary winding connection is same as that of the previous case, so the phasor diagram is same. Now let's draw the secondary side connection phasor diagram, and we know that secondary phasors are drawn parallel to primary side phasors. So let's draw the secondary side VA phasor parallel to primary side VA phasor, and we need to decide the direction. So direction depends on the connections we took from. So on primary side we took the connections from dot ends and secondary side we are taking the connections from dot ends, so direction is same to that of primary phasor. And now we need to decide the terminals. So terminals of VA phasor will be A1 and A2, and here we took the connection from dot end, that is A2, so arrow will point towards A2, so other end will be A1. And now observe that to A2 there will be D1 connection and to A1 there will be C2 connection. Now let's draw the secondary side VB phasor. So secondary side VB phasor will be parallel to primary side VB phasor. So let's draw the secondary side VB phasor somewhere like this, parallel to primary side VB phasor. And now let's decide the direction, and the direction depends on the connection we took from. On both primary side and secondary side the connections are taken from dot ends, so direction is same. And now decide the terminals. As on secondary side we took the connection from dot end, that is B2, so arrow will point towards B2, so other end will be B1. So this is VB phasor. Now come to this phasor diagram. this is having B1 terminal, therefore VB phasor will be drawn like this. Okay, so this is VB phasor. Now let's draw the secondary side VC phasor. So secondary side VC phasor is drawn parallel to primary side VC phasor. So primary side VC phasor is like this. So let's draw the secondary side VC phasor like this, parallel to primary side VC phasor, and decide the direction. So here the connections are we took from dot and terminals. So direction is same as that of primary phasor, and we need to decide the terminals. On secondary side, the external connection is from dot end, that is C2. So arrow will point towards C2 and the other end will be C1. So now coming to the secondary side main diagram. So B2 is having C1 terminal. So place this phasor like this. So this is how to obtain the secondary side delta connected phasor diagram. And as this is delta connection on secondary side, we need to draw the phase to neutral voltage for comparison purpose. So let this be the imaginary neutral in delta connection. And now we need to decide of A2N or A1N is the phasor for comparison. And observe that in VA, the connection is took from A2. So the phase to neutral voltage for comparison purpose is A2N. And now let's identify the vector group symbol for this star delta connection. And we know that in vector group symbol, first character will indicate the HV winding connection, and which is in capital letters. So in vector group symbol, the first character is capital Y, and the vector group symbol second character is in smaller case, and that will indicate the LV side connection. So here we took delta as LV side connection, so it is represented with smaller case d. And now we need to decide the third position of vector group symbol. So here the third position is numerical, and the numerical in third position will indicate the LV side phase to neutral voltage phase displacement with respect to HV side phase to neutral voltage. So now coming to this phasor diagram, observe that in primary side phasor diagram, this is the phase to neutral voltage, and primary side phase to neutral voltage is taken as a reference, and that is represented with minutes needle in clock. And as this is taken as reference, minutes needle is shown always pointing towards 12. And now coming to the secondary side phasor diagram, LV side phase to neutral voltage here is A2N, and which is represented with hours needle in clock. And if you superimpose this on this, then the primary side voltage will look like this, and secondary side phase to neutral voltage of delta connection will look like this. This means if you place this primary side phase to neutral voltage over here, means then the LV side phase to neutral voltage will look like this, and which will be pointing towards 11, means the angle between minutes needle and hours needle is now 30 degrees. It is taken as plus 30, which will indicate that LV side phase to neutral voltage leads by an angle of 30 degrees with respect to HV side phase to neutral voltage. So this is one way of obtaining the star delta connection. So with this connection we got 30 degrees lead phase displacement, and with this connection we got 30 degrees lag displacement. Now let's draw the other possible connection of star delta connection. Star delta connection has 4 possible connections. This is first connection, and this is the second possible connection, and now we are going to see the third possible connection of star delta connection. In these two cases of winding connections, we took the output from dotted end terminals, and now in third and fourth possible connection we are going to take the connections from non-dot ends. Now let's see that. So let this be the LV winding and these be the dotted end terminals, and we know that LV winding notations are given in smaller case, as these are the dotted ends. So this will be small a2, small b2, small c2, and the other ends will be a1, b1 and c1. And now here we are going to connect non-dot end with dot end, and non-dot end with dot end, and similarly here non-dot end with dot end. And here we are taking the connections from non-dot ends. that is A1, B1 and C1. In previous two cases, we took the connection from dot ends, that is from A2, B2 and C2. And here we are taking the connections from non-dot ends. So this is the third possible connection of star delta connection. And the phasor diagram for this winding connection is same as that of the previous two cases because we didn't change any connection. And the difference is only in the LV winding connections. So now let's draw the phasor diagram for delta connected LV winding. And it is known that secondary side phasors are drawn parallel to primary side phasors. So first let's draw the secondary side VA phasor parallel to primary side VA phasor. So let this be the secondary side VA phasor drawn parallel to primary side VA phasor. Now we need to decide the direction of secondary side VA phasor. So direction depends on the connections we took on primary side and secondary side. Okay, here on primary side we took the connection from dot ends, and on secondary side we took the connection from non-dot ends. Means here the secondary side phasor direction will be opposite to primary side phasor. As the primary side phasor direction is upwards, so the secondary side phasor will be downwards. So this is VA phasor. And now we need to decide the terminals for this VA phasor. As here on secondary side we are taking the connections from non-dot ends. Okay, means from A1, B1 and C1. So arrow will point towards the connection we took from. So here arrow will point towards A1. So obviously the other end will be A2. Now let's draw the secondary side VB phasor. So secondary side VB phasor is drawn parallel to primary side VB phasor. Let's draw it somewhere here. And now we need to decide the direction. As the connections on primary side are took on dot end, and on secondary side the connections are took on non-dot end, means the secondary side phasor will be in opposite direction to primary side phasor. So on primary side the VB phasor is towards this direction, means the secondary side VB phasor direction will be like this. And now we need to decide the terminals for this. So here the connection is took from non-dot end. So non-dot end here is B1. So arrow will point towards the connection we took from. Therefore arrow will point towards B1. So other end will be B2. So observe in winding connection that A1 is connected to B2, means here to A1 there will be B2. So now move this phasor like this such that it will have B2 here. Therefore this is VB phasor and this is the B1 end. Now let's draw the secondary side VC phasor. So let this be the secondary side VC phasor drawn parallel to primary side VC phasor. And now we need to decide the direction. As on primary side connections took from dot end, and on secondary side connections took from non-dot end. So here the direction of secondary side phasor will be opposite to primary side phasor. So as the primary side VC phasor is towards this direction, so secondary side VC phasor direction will be like this. And now we need to decide the terminals. On secondary side the winding connections are took from non-dot end, means arrow will point towards the connection we took from, that is C1. So other end will be C2. And observe in winding connection that A2 is having C1 connection, means here to A2 there will be C1 also. So as we got the VC phasor like this, move this phasor such that it is having C1 like this. So this is VC phasor. And now our task is to decide the phase to neutral voltage of delta connection. And we know that there will be no neutral connection in delta connection, but for comparison purpose we need to take imaginary neutral. So let that imaginary neutral be N. And why we need phase to neutral voltage means in vector group symbol the third numerical will indicate the LV voltage phase to neutral voltage displacement with respect to HV winding phase to neutral voltage. Okay, therefore we need here phase to neutral voltage. And now we need to decide which is the phase to neutral voltage. As here in winding connection we took the connection from A1, therefore the phase to neutral voltage will be like this. Now superimpose this secondary side phasor on primary side phasor and observe the phase to neutral voltages of primary side and secondary side. So then the primary side phase to neutral voltage will look like this, and the secondary side phase to neutral voltage will look like this. And now imagine that this diagram is placed in clock such that primary side phase to neutral voltage is pointing towards 12. If this is the clock, so these are the numericals on clock. So placing this diagram such that primary side phase to neutral voltage points towards 12, and this will indicate the 5 o'clock. Here the HV side phase to neutral voltage is represented by minutes needle in clock, and the LV side phase to neutral voltage is represented by hours needle in the clock, and the angular difference between minutes needle and hours needle will give the LV side phase to neutral voltage displacement with respect to primary side phase to neutral voltage. So now let's identify the vector group symbol for this type of connection. In vector group symbol, the first character is represented with capital letter, and that will indicate the HV winding connection. Here on primary side we took the HV winding connection as star. So let's represent that first character with capital Y. And now the second character in vector group symbol represents the LV winding connection, and it is represented in smaller case. Here LV winding connection is delta, so that is represented with small d. And now we need to decide the third position of vector group symbol, which is a numerical, okay, and that is given by clock notation. So for this connection we got 5 o'clock, means the numerical here is 5, and 5 will indicate the LV side phase to neutral voltage displacement with respect to HV side phase to neutral voltage, and that phase angle displacement is given by the angle between minutes needle and hours needle. For 5 o'clock, the angle between minutes needle and hours needle is, if you measure in clockwise direction, it will be 210 degrees, or if you measure in anti-clockwise direction, it will be minus 150 degrees. Therefore, for this type of connection, we are having a phase displacement of 210 degrees, and 210 degrees can be written as 180 degrees plus 30 degrees. Now let's discuss the fourth possible connection of star delta connection. On primary side, the connections are left unchanged for all the four possible connections, and the change here we are making on the secondary side winding connections. And in fourth case, what we are doing, that we are taking the connections from non-dot ends and joining the dot end with non-dot end. Let's see that. So here we are joining the dot end with non-dot end, dot end with non-dot end, dot end with non-dot end, and taking the connections from non-dot ends. So this is the fourth possible connection of star delta connection. And now let's draw the phasor diagram for this. And primary side phasor diagram is same as that of all the previous three cases. And now we need to draw the phasor diagram for the secondary side winding connection, that is for LV winding connection. So secondary side phasor is drawn parallel to primary side phasor. So let's draw the secondary side VA phasor parallel to primary side VA phasor. And now let's decide the direction. On primary side, the connections are took from dot end, and on secondary side, connections are took from non-dot end. Means the secondary side VA phasor will be in opposite direction to primary side VA phasor. So like this. And now let's decide the terminals. So on secondary side, we took the connections from non-dot ends, and that is A1. So arrow will point towards the connection we took from. So arrow will point towards A1. So other end will be A2. Now let's draw the VB phasor. Drawing VB phasor parallel to primary side VB phasor like this. And now we need to decide the direction. And here the primary connections are took on dot ends, and secondary side connections are took from non-dot ends. Means the secondary side VB phasor direction will be opposite to primary side VB phasor. So like this. And now we need to decide the terminals. So here the connections are took from non-dot ends, that is B1. Therefore arrow will point towards the connection we took from, that is B1. So this is B2. Now observe in winding connection that A2 has connection with B1. Therefore here we will obtain B1. So place this phasor such that A2 will be having B1 connection. So like this. Therefore, other end will be B2. Now let's draw the secondary side VC phasor. So let's draw the secondary side VC phasor parallel to primary side VC phasor. And now we need to decide the direction. So here on primary side we took the connection from dot end, and on secondary side connections are took from non-dot end. This means the secondary side VC phasor direction will be opposite to primary side VC phasor. So now the direction of secondary side VC phasor will be like this, opposite to primary side VC phasor. And now we need to decide the terminals. So here on secondary side connections are took on non-dot ends, and here the non-dot end is C1. Therefore phasor points towards the connection we took from. So arrow points towards C1. So obviously the other end will be C2. Now observe in winding connection that B2 has connection of C1. So therefore place this phasor as it is, such that B2 is having connection of C1 and A1 is having connection of C2. And now we need to decide the phase to neutral voltage of delta connection. And we know that in delta connection there will be no neutral connection, but for comparison purpose we are taking the imaginary neutral. So here let that be small n. And now we need to decide the phase to neutral voltage of delta connection. So here the connections are took from A1. Therefore the phase to neutral voltage will be A1n. Now superimpose this diagram on this and observe the primary side phase to neutral voltage and secondary side phase to neutral voltage. Therefore the primary side phase to neutral voltage and secondary side phase to neutral voltage will look like this. In vector group symbol, the numerical will indicate the LB winding phase to neutral voltage phase displacement with respect to HV winding phase to neutral voltage. So here this is LV winding phase to neutral voltage and this is HV winding phase to neutral voltage. Okay. And HV side phase to neutral voltage is represented with minutes needle in clock, and LV side phase to neutral voltage is represented with hours needle in clock, and the corresponding clock hour that is obtained is the numerical in vector group symbol. Therefore place this diagram in clock such that primary side phase to neutral voltage will point towards 12, because primary side phase to neutral voltage is always taken as reference, so is why it is always shown pointing towards 12. And now if you place this diagram such that phase to neutral voltage is pointing towards 12, then the diagram will look like this, and this represents the 7 o'clock. So now let's identify the vector group symbol. In vector group symbol, the first character is in capital letters, and that will represent the HV winding connection. Here we took HV winding as star, so the first character is represented in capital letter, and that will represent the winding connection, therefore capital Y. And now the second character in vector group symbol will indicate the LV winding connection, and that is represented in smaller case, so here delta, therefore small d. And for this connection we got the numerical as 7. The angle between minutes needle and hours needle here is, if you measure in clockwise direction, it will be 150 degrees, or you can write it as 180 degrees minus 30 degrees. Therefore for this type of star delta connection we are having a phase displacement of 150 degrees. Therefore with star delta connection we are obtaining the phase displacement of plus or minus 30 degrees and 180 degrees plus or minus 30 degrees. And this phase displacement always indicate the LV side phase to neutral voltage displacement with respect to HV side phase to neutral voltage, irrespective of what is primary and secondary. Now let me draw all the 4 possible connections of star delta connection, so that it will be easy for you to remember those connections. Let these 3 be the HV windings, and let these 3 be the LV windings, and let these be the dot end terminals. And we know that HV winding terminals are represented in caps, that is A2, B2 and C2. Therefore these ends will be A1, B1 and C1, and LV winding terminals are represented in smaller case. So this is A2, B2 and C2. these elements will be A1, B1 and C1. And for all the 4 possible connections, we left the primary side winding connections as it is. So let's draw the all 4 secondary side windings. Therefore, these are the dot ends. Therefore, this will be A1, A2, B1, B2, C1, C2. This will be A1, A2, B1, B2, C1, C2. This will be A1, A2, B1, B2, C1, C2. Here, for first 2 possible connections, we are taking the connections from dot ends. So extend these like this, so that it will be easier for you to say that these are the connections we are taking from. And for the 3rd and 4th possible connections, we are taking the connections from non-dot ends. So extend these non-dot ends like this. And now observe that here what we are doing means, in first case we are joining the non-dot end with dot end. So non-dot end with dot end and non-dot end with dot end. But for the second possible connection, what we are doing means we are joining the dot end with non-dot end, dot end with non-dot end and dot end with non-dot end. Here we join the non-dot end with dot end and here we join dot end with non-dot end. So these are the first 2 possible connections of star delta. And now coming to this case, so here first join the non-dot end with dot end, non-dot end with dot end and non-dot end with dot end. Okay, and for 4th possible connection, join the dot end with non-dot end, dot end with non-dot end and dot end with non-dot end. And the primary side connection is star. And here what we are doing means we are joining the non-dot ends together and taking the connections from dot ends. And this primary side connection is common to all the remaining 3 connections. And we are leaving that connection as it is without any changes. And the changes that you will observe only in secondary side winding connections. So these are the 4 possible connections of star delta connection. From each connection we will get different phase displacement. Now let's know the phase voltage ratio, which can be taken as equal to turns ratio, that is similar to that of single phase transformer, and which is represented with K. So that is equal to N2 by N1. Let small v2 be secondary side phase voltage and small v1 be primary side phase voltage, and here N2 represents the secondary side number of turns and N1 represents the primary side number of turns. So here phase voltage ratio can be taken as equal to small v2 by small v1. And now let's know the line voltage ratio. Let v2 be the secondary side line voltage and let v1 be the primary side line voltage. So v2 secondary line voltage and v1 primary line voltage. The secondary side connection is delta. Therefore, the relation between line voltage and phase voltage for delta connection is that line voltage is equal to phase voltage. So here line voltage we took is V2 on secondary side and the phase voltage on secondary side we took is small v2. Therefore, this is one relation. And now observe the primary side connection. Okay, primary side connection is star. So the relation between the line voltage and phase voltage for star connection is that line voltage is equal to √3 times phase voltage. So primary side line voltage we took V1, which is equal to √3 times phase voltage. Primary side phase voltage is small v1. Therefore, this is the other relation. Now in line voltage ratio, replace the line voltages with the phase voltages, that is equal to small v2 by √3 times small v1, and we can take that 1 by root 3 into small v2 by small v1 can be taken as equal to k. That implies line voltage ratio is equal to v2 by v1 is equal to 1 by root 3 times k. That implies v2 is equal to v1 by root 3 into k. Now if you observe from this relation that secondary side voltage is less when compared with primary side voltage, that is, it is 57.7% of primary side voltage. It means this type of connection is used for step down applications, and the advantages of this connection are that this connection is economical for large high voltage transformers, and the second advantage is, as the primaries star connected, fewer turns are required. And here on primary there is star connection, so by providing neutral connection, distortion in output can be avoided. And here the other advantage is no third harmonic problem, as here this type of connection is having delta connection on secondary side, so there will be no third harmonic problem, and unbalanced load can be handled. So these are the advantages of this star delta connection. And now the disadvantage of this connection is that it can't be paralleled with other transformers having different phase displacement, which means that to operate transformers in parallel, all the transformers must have same phase displacement. And now the application is, from the line voltage relation, we seen that the secondary side voltage is less when compared with the primary side voltage, which means that this type of connection is employed for step down applications. Means here the application of star delta connection is on substation and to step down the voltage. This is about star delta connection.